you will be learning how to analyze the PSC beam for shear and how to design a PSC beam for a given shear force. Okay, so both the things we will be learning in this module. That is the course outcome. Okay, you will be able to analyze the PSC beam for shear, and you will also be able to design the PSC beam for the given shear force. Okay. So here also the basic principle used behind analysis for shear is same only. Whatever you used to practice in strength of materials for normal RCC beam for analyzing for the shear, the same principle here we will be using, but in consideration with the effect of pre-stressing force, we will find the shear resistance, ultimate shear resistance of the PSC beam. Okay, along with the normal loads, this PSC beam will also have the pre-stressing force. Okay, effect of pre-stressing force will also be there. Okay, which will contribute towards increasing the shear resistance of the beam. Okay, including the effect of pre-stressing force, we will find the shear resistance. Okay, and this formula you already aware. It's a very general formula. In third semester only you have learned about this formula. Okay, the shear stress at a point on a beam tau v is equal to Vu into Ay bar divided by I into B, where Vu is the shear force. Okay, and A is the area of the cross section, and Y bar is the distance of the centroid. Okay, of the section from the neutral axis. Okay, this multiplication of or product of this A into Y bar is nothing but first moment of area. Okay, or static moment of area. Sometimes we will also denote it by the letter S. Okay, and I you already know it is moment of inertia, and B is width of beam. Okay, in case of flanged sections, in place of B we'll take BW. Okay, width of web we'll consider for the calculations. Okay, so in the problem it will also be asked to find the principal stresses. Okay, these formulae also you have derived and you have very well thorough with these formulae in your strength of materials. In the problems, it will also be asked to find the principal stresses. If the principal stresses is asked, so you need to utilize this formula. Okay, fx plus fy whole divided by 2 plus or minus half root of fx minus fy whole square plus 4 into tau v square. Okay, using this formula, you will find principal stresses where fx is the horizontal pre-stress, fx, okay, stress in x direction. Okay, which is calculated by force pre-stressing force divided by cross sectional area, and Fy is the vertical pre-stress. Okay, sometimes pre-stressing will be done for a beam in the vertical direction also. Till now we have seen pre-stressing in the horizontal direction. If it is required, pre-stressing is also done in the vertical direction as well. Okay, means the pre-stressing wires will be provided in the vertical direction also. Okay, and here is the cross section of the beam. Okay, and coming to the flanged section, ultimate shear resistance is determined by using this formula. Vc naught is equal to 0.67 bd into ft square plus 0.8 fcp into ft. Okay, where ft is tensile stress of the concrete. Sometimes it will be directly given. If it is not given, fck will be given. By using this formula, we can find what is the value of ft. Okay, in page number 46 of IS 1343 1980, this formula is available. Okay, for finding the ft, 0.24 root of fck. This formula is available in the page number 46. Okay, fcp is the compressive stress in concrete at central axis, which is equal to load by area, pre-stressing force divided by cross sectional area. Okay, so along with, and this formula is also available in page number 46 of IS 1343 codebook. Along with this formula, there's one more formula that we will use. Here we have Vc naught is equal to Bw into I by S, where S is static moment of area, that is Ay bar, Ft square plus Fcp into Ft. Okay, we will use this formula to find the ultimate shear resistance. okay, of the I section. Okay, this is the simplified formula, and you can you have to remember this formula. This formula is not there in the code book. Okay, this is the simplest way of find using this formula. You can easily find the value of ultimate shear force or ultimate shear resistance. Okay, we'll be utilizing this formula in the next calculations when solving the numerical problems. Okay, all of you remember this formula: BW into I by S root of FT square plus FCP into FT. Okay. Okay, with this, I'll directly go to solving the problems. Okay, let us take the first problem. All of you write this problem. Take 1 minute time to write the problem. Take 1 minute time to write the problem.
ಆ ರೆಕಾರ್ಡ್ ತೋರಿಸ್ಬೇಕು ನಾವು ಅಷ್ಟಾಗಿ ಗಮನಿಸ್ತೀವಿ ಅಷ್ಟೇ ಸಾಫ್ಟ್ ಕಾಪಿ.
All of you write this problem. Okay, in this model, directly the numerical problems will be asked. Okay, there will not be any theory questions. Okay. You just go through the problem. A concrete beam. So a concrete beam of rectangular section 200 mm wide and 650 mm deep is pre-stressed by a parabolic cable located at an eccentricity of 120 mm at midspan and 0 at the supports. Okay, first write the diagram. Okay, write the cross-sectional dimensions. Also write the longitudinal section solution. What is the cross section of the beam given? 200 by 650. By 650 is the cross section of the beam given in the problem. Okay, and the cable provided, pre-stressing cable provided in the beam is a parabolic cable with some eccentricity at the midspan and 0 eccentricity at the support. Let me write the diagram for the same. Also draw the central axis. Central axis. So what is the profile of the cable explained here? He says that the parabolic cable located at an eccentricity of 120 mm at the midspan and 0 at the supports. Okay, the cable eccentricity is 0 at the supports and 120 mm at the midspan. Okay, 0 at the supports, 120 mm at the midspan. E is equal to 120 mm. E is equal to 120 mm. Okay. Then and carries a uniformly distributed live load of 4.5 kilonewton per meter. The live load on the beam is given. How much it is? 4.5 kilonewton per meter. Write that. Live load on the beam is 4.5 kilonewton per meter. Okay. Now coming to the question, find the effective force necessary in the cable. Okay. We have to find the effective force P necessary in the cable. Necessary in the cable for zero shear stress at the support section. Okay, we have to find a suitable prestressing force, magnitude of the prestressing force. Okay, suitable magnitude of the prestressing force, which will cause zero shear stress at the support section. That is the first question. Okay, with OB is equal to 0. Okay, we have to find the magnitude of the prestressing force P with the condition shear stress at the support is equal to 0. That's the first question. For this condition, calculate the principal stresses, means sigma minimum and sigma maximum. Here I shown you the principal stresses we need to find. There is that formula. Here we have the formula sigma maximum and sigma minimum we need to find. That is the second question. Sigma max and sigma minimum. We have to find. This is the second question. Now we will take the first question. Okay. First question. First question to find the value of prestressing force P with shear stress at the support is equal to 0. Okay, so we need to utilize this condition. Tau v equal to 0 condition we need to utilize now. Okay, now I'll take the same condition. Given condition is shear stress at the support equal to 0. It is a given condition. Okay, what is the formula for shear stress? Formula for shear stress is Vu into Ay bar divided by Ib, right? Vu into Ay bar divided by Ib is equal to 0. Is equal to 0. The shear stress at the support equal to 0. Now you find one by one each and every parameter. First you find the Vu. What is Vu? Vu is shear force at the support. Okay, Vu is nothing but shear force at the support. To find shear force at the support, the live load on the beam is given. Dead load it is not given, means self weight it is not given. You need to find it. You need to find the self weight of the beam. Okay, dead load on the beam, dead load plus live load will give total load that is acting on the beam. By knowing total load, you can find the shear force. Correct. Now below you write dead load of the beam is equal to dead load of beam is equal to what is the how we will find it? Cross sectional area multiplied by density. Okay, cross sectional area multiplied by density is equal to what is the cross sectional area? 200 by 650 means 0.20 into 0.65 into density of the concrete is 24 kilonewton per meter cube. If you multiply all the values, so you will get the answer as 3.12 kilonewton per meter. Okay, and live load on the beam is given in the problem only. Live load on the beam, how much it is given? 4.5 kilonewton per meter. 4.5 kilonewton per meter. Now you can calculate the total load. Total UDL is equal to 3.12 plus 4.5. How much? It is 7.62. 7.62 kilonewton per meter. Okay. So now total UDL is known. You can calculate the ultimate load now. Therefore, ultimate load or factor load is equal to ultimate load is equal to 7.62 into factor of safety of 1.5. How much you'll get? You'll get it as 11.43. Okay, 11.43 kilonewton per meter. Okay, if you are getting any different answer, let me know. Okay, we'll correct it. Now total ultimate load acting on the beam is 11.43 kilonewton per meter. Now you can find the shear force. Write the diagram. And beam is simply supported. Okay, it is understood only. The total factor load or ultimate load acting on the beam is how much? It is 11.43 kilonewton per meter, and that length of the beam. What is the length of the beam given? Length of the beam is having 12 meter. 12 meter is the span of the beam. Okay, so below right, 12 meter is the length of the beam. What is the shear force at the support then? Whatever the reaction that you get, that will be the shear force, correct? Therefore, reaction at support is equal to WL by 2, total load divided by 2. Okay, 11.43 into 12 divided by 2. The answer that you get is 68.58 kilonewton. 58 kilonewton. Okay, 68.58 kilonewton. Now the shear force at the support is how much? 68.58 kilonewton. Okay, so at the beginning only I told we have to consider the effect of pre-stressing force also while doing the calculations. Okay, if there is only load acting on the beam, the shear force at the support is 68.58 kilonewton. There is no only the effect of dead load and the load. There is effect of pre-stressing force also. So we have to find the vertical component of pre-stressing force at the support also here. Okay, we have to find vertical component of the pre-stressing force also. For example, here P is the force acting through the cable, correct? So what is its vertical component? Its vertical component will be P sin theta. Okay, its vertical component will be P sin theta, and this P sin theta vertical component of the pre-stressing force should be added with the reaction at the support. Finally, you will get the shear force VU at the support. Okay, I hope you are understanding. You have to consider the effect of pre-stressing force also along with the effect of the dead load and the lay load. Okay, the net shear force due to dead load and lay load is how much? Plus 68.58 kilonewton. Okay, now we need to calculate what is the vertical component of this P sin theta. Okay, vertical component of this pre-stressing force P. Okay, now there is a standard formula for finding this vertical component. Let me show you. See, for P sin theta, this sin theta value, no, here I written, just you need to remember. See, if it is a parabola, sin theta is nothing but what? Sin theta is nothing but slope. Okay, it is nothing but slope of the cable. Okay, see, if it is the parabolic cable, okay, the value of sin theta is equal to 4E by L, where E is eccentricity at the midspan. Okay, sin theta value is calculated as 4E by L. If it is a linear cable, then sin theta value will be E by L by 2. E by L by 2. Okay, so actually this calculation represents the tan theta. See, whatever the slope at the support, it is assumed to be very negligible. When the slope is very negligible, almost the sine function is equal to tan function. That is why instead of taking tan function, we are taking sine function here. Okay, sine theta is equal to E by E whole divided by L by 2. Finally, you will get 2E by L. Okay, if it is a parabolic cable, you need to take 4E by L as sine theta. Okay, if it is a linear cable, you need to take 2E by L as sine theta value. Okay, now sine theta value is what? 4E by L. Here, whatever the cable given here, it is a parabolic cable. So sine theta value is equal to 4E by L. Okay. The vertical component of pre-stressing force. Okay. Pre-stressing force is equal to P sin theta. P sin theta. Okay. Where sin theta value is what? It is 4E by L for parabolic cable. Slope of parabolic cable. Okay. P into 4E by L. So it is equal to P into 4 into what is eccentricity at the midspan? It is 120 mm. Substitute. So 120 mm divided by length of the beam. Length of the beam is given as 12 meter. See, eccentricity we are substituting in terms of millimeter. We substitute the length of the beam in terms of mm only. So 12 meter means 12,000 millimeter. 12,000 millimeter. So finally, after simplification, you will get this value as 0.04 P. Okay, 0.04 P. And what is the direction of this P sin theta? It is downward. It is downward. What is the direction of the reaction? It is upward. It is upwards. Now we have to add both the values to get the net shear force. Okay, we have to add both the values to get the net ultimate shear force. Therefore, net ultimate shear force VU is equal to plus upward means plus. Okay, upward 68.58 plus 68.58 minus 0.04 P. Minus 0.04 P. Okay, this is the value of net ultimate shear force at the support. Now we got the value of VU. What is next required? We require the value of this AY bar. Okay. Okay. First moment of area. Okay, or the static moment of area, we need A into Y bar. For that, you write a small diagram once again to find AY bar. So this is the cross section. Okay. Neutral axis, you write. So here static moment of area about the neutral axis. We need to find about the neutral axis. So here width is given as 200 and overall depth is 650. Overall depth is 650 means half of the depth means here we'll get 325 mm. 325 mm. Okay. So distance of centroid of this area from the neutral axis will be how much? It will be 325 divided by 2. Okay, it will be 325 by 2. Okay. Now AY bar is equal to area of PSC beam above the neutral axis. What is the area of PSC beam above the neutral axis? It is 200 into 325. 200 into 325 into distance of Y bar. Y bar is the distance of centered of hatched portion from the neutral axis. It is into 325 divided by 2. Okay. What is the answer that you get? The answer will be please cross check the answer. 10.56 into 10 power 6. 10.56 into 10 power 6. Okay, 10.56 into 10 power 6. The unit will be mm cube. Mm cube. Okay, now you got the value of Ay bar. What else is needed? Moment of inertia is needed. You know the formula for moment of inertia of a rectangular section. I is equal to BDQ by 12. So B is 200 into overall depth is 650 Q by 12. Okay. It is 4.6 into 10 power 9 mm to the power of 4. Mm to the power of 4. Now you got all the required values. Okay. You call this as equation number 1. So equation 1 becomes VU into AY bar divided by IB. VU is equal to how much? VU is equal to 68.58 minus 0.04 P. 68.58 minus 0.04 P. VU into AY bar. AY bar value is 10.56 into 10 power 6 divided by IB. 4.6 into 10 power 9 into width of the beam is 200 is equal to 0. Is equal to 0. Okay. So here P is only the unknown parameter, correct? We can solve for P. If we solve for P, the value that you get is P is equal to 1714.5 kilonewton. Okay, 1714.5 kilonewton is the answer. 1714.5. Okay. Then with this we have solved the first question. With this we have solved the first question. Then we'll go for the next question. The principal stresses. Okay. Principal stresses. Write the line. Principal stresses. Principal stresses. Principal stresses. So formula, just write the formula. Sigma max. Formula for principal stress. Sigma max or sigma minimum. This formula you need to remember, students. Fx plus Fy by 2 divided by 2 plus or minus half of root of Fx minus Fy whole square plus 4 to V square. 4 to V square. Okay. Now we need Fx. Fx means stress in the x direction. Directly it is pre-stressing force divided by area. Pre-stress in the x direction. P is just before we have calculated, that is 1714.5 kilonewton. 1714.5 into 10 power 3 Newton divided by area of cross section is how much? It is 200 into 650. The answer that you get is Fx equal to 13.18 Newton per mm square. Okay, that is horizontal pre-stress. Okay. Now you got the fx value. Next is fy value. Fy, there is no pre-stressing steel or pre-stress in the y direction, that fy value is taken as 0. Okay. If there is some pre-stresses or pre-stressing steel given in the y direction, that we can calculate. Okay. So in this particular problem, fy is 0. There is no vertical pre-stresses. There is no vertical pre-stress. Okay. Fi equal to 0, then what else you need? Tau v, it is said as 0 only. In the condition, that condition only given, tau v equal to 0. Now you can substitute everything. Therefore, sigma max is equal to fx plus fy whole divided by 2. That is 13.18 plus fy is 0 whole divided by 2 plus. Okay, if you want to get the maximum principal stress, you need to take the plus side. Fx is 13.18 minus fy 0 whole square plus 4 tau v square, 4 into 0 square. So the answer that you get is 13.18 Newton per mm square. Okay, and sigma minimum on capital 13.18 Newton per mm square. Then sigma minimum, if you want to calculate the sigma minimum, same data, here negative sign will come, root of, let me write it, 13.18 plus 0 divided by 2 minus of 13.18 minus 0 whole square plus 0. Answer is, so you will get 0 only. If you calculate the answer, you will get 0 answer only. Okay. So to this, this problem is over. If you have got any doubts at any point of the calculation, you can ask students. Any doubts in this problem? Okay, thank you.